we are going to be looking at another interesting topic, and that topic is oxidation reduction reactions. Oxidation reduction reaction, and sometimes some people will feel like calling it redox reaction. However, you want to call it, whether I want to call it as oxidation reduction reactions or I want to call it as redox reaction, it is still fine. Now, do you know that oxidation reduction reactions play a very significant role in chemistry, and not just in the aspect of chemistry, but chemistry of various various levels. Now, in our day-to-day activities, we come by the oxidation reduction reactions. The truth of the matter remains that you cannot even find a chemical reaction that is not a redox reaction. A chemical reaction will be such that it's either is a one-way reaction where oxidation plays a role, or a one-way reaction where reduction plays a role, or a two-way reaction where both the oxidation and reduction are playing their role in that reaction. And that is what you even call redox reaction. Okay, now you can find oxidation reactions happening in photosynthesis. Now, you know much about photosynthesis, but in case you do not have an idea, but this is a process where plants manufacture their food through the help of sunlight and some extent oxygen and thereabout. Now, this process is carried out with the understanding that there is oxidation reactions that take place there, and there are also reduction reactions that takes place there. Again, you can see combustion reactions also showing you some level of oxidation reactions. And how about cellular respiration? Even in cellular respiration, okay, where you and I take part in respiration, you also see the oxidation reduction reactions also playing their role, and most importantly in corrosion science. Do you know that the process by which a nail gets itself corroded and bring out a product you call rust is entirely an electrochemical process, and that electrochemical process is a corrosion process, and it is an oxidation reduction process. But of course, if there is no oxidation in that particular corrosion process, then there will be no form of corrosion itself taking place, because of course corrosion is as a result of the possible disintegration. Okay, let me use that term, disintegration, or washing away or dissolution of the anodic part of a particular process setup. Okay, and then that particular dissolution is what allows for corrosion. Now, that dissolution is only possible because of the presence of oxidation reaction. Now, oxidation takes place at the anodic end of that particular type of reaction. Now, for still under that electrochemical reaction, reduction takes place at the cathodic end. The cathodic end experiences hydrogen evolution, which gives rise to hydrogen embrittlement. And this also allows for corrosion to take place. So, corrosion, as much as we talk about others like photosynthesis, like solar respiration, and a lot, combustion, all of them experiences oxidation reduction reaction. So every kind of chemical reaction that happens, whether in the lab or natural, experiences oxidation reduction reactions. Now, take a look at the diagram that we have on the board here that quickly try to highlight what oxidation and reduction is all about. Now, I want us to know that usually or mostly we understand oxidation and reduction from the classical approach of its definition. Okay, so when you look at the classical approach of the definition or the understanding of oxidation reduction reactions, you begin to look at the addition of oxygen and removal of hydrogen. That is what we know. That is a common term, the common definition of oxidation reduction reactions that we know. Addition of oxygen, removal of hydrogen. That is the classical or the Renaissance approach of looking. I am not saying that it's wrong, okay, but there are other approaches you can look at oxidation reduction, because there are some reactions that may not have anything to do with addition of oxygen or removal of hydrogen. So you look at other approaches, especially the electronic approach or the modern approach of understanding oxidation reduction reactions. So we are going to look at all this and bring us to light how we can be able to identify a reaction to be oxidized, or a species or compound in a reaction to be oxidized or to be reduced. Now, if we take a look at this is actually using the electronic or even the modern approach to discuss the oxidation reduction reaction, because that modern approach or electronic approach builds on the gaining or the losing of electron. Now, when you take a look at what we have on the board here, this is a species A, which can be an element or can even be a compound, as the case may be. So this is species A, species B, giving rise to another the product A and a product B. Now, if you take a look at this diagram, you notice that these species are having they are in their elemental form, because it's only in the elemental form that they come with zero charges. Now, there is a show of transfer of electron from A to B in the process. Now, with the transfer of electron from A to B, it is going to cause what? It's going to cause an oxidation of A, because in that case A have lost electron, while B gain electron. Now, as A have lost electron, by that transfer of electron, it makes it more electropositive, and it becomes the oxidizing species. Now, the B that accepts the electron now makes itself more electronegative and becomes the reduced species. And that is why from this diagram you can see that A in an elemental form with zero oxidation number, as the case may be, is losing electron in the process, and because it loses electron to B, it becomes more electropositive, and we said it is what? It is oxidized. And the B that gain, it is what? More electronegative, therefore it is what? Reduced. Now, this is a typical way of looking at oxidation reaction, understanding what species is oxidized and what species is reduced. Now, we are going to use chemical equations, for example, to highlight, to drive our point home on how we can understand when we say species are oxidized, compounds are reduced under different conditions, and not just on the classical approach or recent approach of this very understanding. Okay, now let us take a look at that. Now, we have about 4 different ways by which we can be able to classify species species or compounds being oxidized or being reduced. Now, let us look at oxidation, for example. Trying to define oxidation, trying to look at species that are oxidized and the ones that are reduced, we look at the 4 perspectives. Now, the first perspective is that we are going to look at it from the classical approach, which is gain of oxygen. Gain of oxygen. And we look at it now, looking at it from the modern way, the electronic approach. Okay, one of the electronic approaches we are going to be looking at. So we can also be looking at it from let's say loss of electron. Okay, so loss of electron. Okay, so we can also look at it from let's say removal of hydrogen, and then we look at it also from the aspect of increase in oxidation number. Okay, now these are the 4 possible approaches to which you will be able to comfortably define or describe a species or a compound to be oxidized or to be reduced in a reaction. Whether it is a redox reaction where both oxidation and reduction are taking place at the same time, or it's a unidirectional reaction where you can have only oxidation or reduction taking place. But in whichever way, these are the 4 basic ways, and you must know that these 3 basic ways that you have here are the modern or electronic approach of understanding oxidation reduction reaction, except for the gain of oxygen, which is of course the Renaissance or the classical approach. Now, if you have, for example, 4 iron plus 3O2, okay, to give you 2 iron, and then O3. Okay, let's use that. Let's use that. Okay. Now, if you take a look at this, reaction, if we are trying to look at what species is actually oxidized and which one is actually reduced, because this is a typical redox reaction. Now, if we are defining on the basis of gain of oxygen, which is a classical approach, and that is quite a very simple one, you will take a look at this equation and notice that this iron, 4 molecules of iron reacting with 3 molecules of oxygen give us this. This is iron 3 oxide. Of course, this is a product of corrosion from oxidation reaction, which is rust. This is rust. The hydrated form is what is rust. Okay, now if you take a look at this, you will see that in this reaction, oxygen is added to iron. Yes, and it's more like saying where you have addition of where you have increase of electro positivity, you define it as oxidation. When you have decrease in when you have an increase in electronegativity, you define it as what? As reduction. That is, say, where you have electronegativity you have electronegative element, of course, being added in a particular reaction, you define that as what? As being oxidation. But where you have electropositive metal being added to a particular compound, you define it as what? As reduction. Now, away from that, this is oxygen, and we are saying where there is gain of oxygen by a compound or even a species, it is defined as oxidation. With an equation like this, oxygen is added to what? To iron. So iron as a species has gained oxygen from here, and that is why you now have the compound form as iron 3 oxide. In this way, you can possibly say that iron is oxidized, why oxygen is reduced. Oxygen is reduced, of course, because from here, oxygen is what added itself to the iron. Therefore, iron gained oxygen, so iron is oxidized, oxygen is reduced. This is a very simple way to understand this. Now, but when time went on, and we noticed that it is not all about oxygen addition. There are lots of reactions that do not even have oxygen in their presence. But how do you go about them to understanding whether they are oxidized or reduced? That the issue of loss of electrons or gain of electrons, removal of hydrogen, or increase in oxidation carried. Of course, these two are the ones in the electronic or modern approach were able to explain to a reasonable extent oxidation reduction for reactions that do not even have oxygen. Even the ones that has, it makes it easier for you to be able to understand. Now let us take a look at this very one here, which is, let's take a look at this, which is loss of electrons. Okay, how do we define loss of electrons in this kind of a process? Now I want us to look at something here. If we are taking a look at this very type of equation, if you are taking a look at this very equation, plus 3O2 to give us 2 iron O3, if we are defining oxidation and reduction on the basis of loss of electrons, just like the diagram that we just erased, the one we began with, you will notice that iron is 4, but iron is 2 here. Okay, iron is 4 here, look at it, and iron is 2 here. Obviously, it shows that there is what? There is a loss of 2 electrons. Now, the loss of 2 electrons is already letting you know that because iron have lost 2 electrons, iron is oxidized. Now, it does not matter again whether it is the addition of oxygen or the removal of hydrogen. But here it is very simple that iron has lost 2 electrons, and now here we have 2 iron. Therefore, because it loses 2 electrons, it is what? It is oxidized. And that is it. You can also look at another example where you have iron giving you iron 2 plus 2 electron. If you take a look at this equation, you will know that it's oxidation reaction, because here iron has lost 2 electrons. Did you see? Iron has lost 2 electrons here. 2 electrons it has lost, and because it lost 2 electrons, it is oxidized. Now, you can conveniently explain oxidation and of course reduction from loss of electrons. And this can be done even with reactions, redox reactions that do not have oxygen involved. And that is why these two modern and electronic methods or approaches to explain oxidation reduction became very important in the area of chemistry. Now, that is by the corner. Now, how about the removal of hydrogen, which of course is still telling us about the Renaissance or even the classical approach, which of course is still in use. Now, if we look at the removal of hydrogen, you can possibly also have a reaction that explains that, where perhaps you have, let's say you have 2 of hydrogen, okay, then you are adding the plus oxygen, okay, and then it's giving you 2 of, let's say 2 of sulfur, okay, plus let's say water, okay, plus water. Now you have an equation like this, hydrogen sulfide, okay. So you have an equation like this where hydrogen sulfide reacting with oxygen, giving you an equation of this nature. Let's balance it. Okay. Now, if you take a look at this kind of a reaction, you also notice that this reaction that you have here is an oxidation reduction reaction. It's a redox reaction. But deeply into this, you notice that this was hydrogen sulfide, which is a compound. But here you have sulfur. That means there is a removal of what? Of hydrogen for hydrogen sulfide. But of course, as much as hydrogen is removed from hydrogen sulfide, that particular species or compound where hydrogen is removed is therefore seen as what? As an oxidizing, as being oxidized. So it means that hydrogen sulfide is oxidized while the oxygen is reduced. That's what it means. That's what it means. So here we are looking at removal of what? Hydrogen. Here we have looked at what? At addition of oxygen. And here we are looking at removal of what? Hydrogen. So it is simple. As far as sulfur in hydrogen sulfide have lost its hydrogen from here, it means that hydrogen sulfide is that compound that is oxidized. And it can go on and on and on and on. Can go on and on and on. And we can also try to look at increase in oxidation number. Okay, now let's see increase in oxidation number, the role it plays, or how we can be able to use that to also explain oxidation reduction reactions. Okay, so we look at increase in oxidation number. So if you were having, for example, you can have the equation, we can still use this. Let's say iron, okay, and giving us iron 2 plus 2 electrons. Can still use this. Okay, and with this, you can also understand the fact that increase in oxidation number shows oxidation. Now, this is iron, an elemental form of iron. Remember that iron is a transition metal and it undergoes variable oxidation state. So you have iron 2, you have iron 3, as the case may be. So in its elemental form, it is able to do what? To lose electron and gain its charges. So here there is an increase in oxidation number. from 0 to +2. Okay, and then there is a losing of what? Of electron. As far as there is an increase in oxidation number, you can affirm the fact that this particular reaction is an oxidation reaction. The ion has been oxidized from 0 to +2, as the case may be. So you can see that even without the presence of oxygen, you can comfortably and conveniently be able to describe or identify which species or which compound is actually oxidized and which one is actually reduced. And then from here, we have arrived at the conclusion that through the gain of oxygen, through the loss of electron, through removal of hydrogen, increase in oxidation state, we can be able to conveniently describe oxidized reactions and reduced reactions. And now, very importantly, we can rely conveniently on the loss of electron and on the increase in oxidation number to define that. Now, if we are looking at reduction, the opposite will now play the role. Because if it is reduction, then we are talking about loss of addition of hydrogen. We are talking about gain of electrons. We are talking about addition, or rather removal of oxygen. And then we are also talking about decrease in oxidation number. That is for reduction. So for reduction is the opposite of oxidation. So for you to identify a species that is reduced, then it means that you must understand if there is addition of hydrogen, or if there is a gain in electron, or if there is removal of oxygen, or a decrease in oxidation number. With this, you can be able to identify what species is actually is actually oxidized, and what species is actually reduced. Now, if we take a look at this kind of a reaction where we have CH2, okay, giving us CH2 plus hydrogen, giving us this 3C and CH3. Now, if you take a look at this reaction, you will see that in this reaction, hydrogen is added to the reaction. So you see that addition of hydrogen has moved this compound, which of course this ethene, has moved ethene to what? To ethane. This hydrogenation of alkane. Okay, this hydrogenation of alkane. So you add more hydrogen to ethene, and then hydrogenation of alkene. So you add more hydrogen to an alkene, and you're going to have an alkane. Now here there is addition of hydrogen, and because of the addition of hydrogen, you can possibly describe this equation as being what? Reduced. So it means that what? It means that alkane, which is ethene, okay, has been reduced to what? To an alkane, which is what? An ethane. Now that is a typical example of that. You can also see more of all this stuff. So when you have probably mercury, you can also have let's say you have 2 of mercury oxide disintegrating to give you 2 of mercury plus oxygen. Now you can have equation of this nature. You have 2 of mercury oxide disintegrating by thermal disintegration to give you mercury and oxygen. If you look at this equation, you will notice that in this equation you have mercury, okay, is 2 and oxygen is 2. But very importantly, we had said that removal of oxygen is what? Is reduction. So here your oxygen has been removed. You can see it. So with the removal of this oxygen, it means that mercury oxide is actually what? Reduced. So in this equation, this is reduced. because there is what? A removal of oxygen against addition of oxygen for oxidation. So these are typical situations, these are typical reactions that throw us every day off balance. To be able to identify, to be able to interpret in certain chemical reactions that are given, which one is oxidized, which one is reduced. Today, I'm sure that we'll make justice to this very topic. Today, I'm sure that after this class, you will be able to use, most importantly, the electronic approach or the modern approach, which is the loss of electrons and increase in ionization number, to be able to explain what species, what compound in a given chemical reaction is oxidized and is reduced. Now, in our next class, we'll try to look at how we can calculate oxidation number from oxidation states, of oxidation states rather, from oxidation number of certain species. Now, do not forget that you have to share. Do not forget that you have to also like and subscribe. And please, when you share this class, please endeavor to subscribe. The YouTube channel remains Dr. B Science Classes. Even on Facebook is that Dr. B Science Classes. When you share, do not forget to ask them, your friends, to subscribe.